This is the story of Lion Air Flight 610. The crash of the Lion Air 737 MAX has been in the public eye unlike any other air crash since the disappearance of MH370. The crash was the first of two that led to the global grounding of the 737 MAX type. This video will be an explainer on what happened to the aircraft. All information presented in this video will be based on the final report published by the Indonesian National Transport Safety Committee. I request that you keep all comments civil, as some of our viewers might have been personally affected by this tragedy. On the 29th of October 2018, a 737 MAX was on the ground at Soekarno-Hatta International Airport, heading to Depati Amir Airport. The crew, prior to takeoff, talked among themselves about the route, the plane, and they talked about the taxiways that they were going to be using. They talked about the ADI, or the automatic direction finder of the plane, which was broken. All in all, it was a pretty routine cockpit. From the cockpit voice recorders, it is clear that the captain was the pilot flying and that the co-pilot was the one monitoring the flight. At 11:15 p.m. UTC, the pilots went through their before taxi checklist, of which a major step is to set the pitch trim. Trim is an aviation term. When a pilot trims an airplane, it frees him or her up from exerting a constant pressure on the control column. For example, if a plane were to be taking off, the pilot would trim the plane to nose up. So when the time came, the pilot would not have to exert a lot of force on the control column, as the trim would deflect the elevators of the plane to slightly pitch up the plane. At 11:18 p.m., the tower gives Flight 610 permission to line up on runway 25 left, and the pilots did their before takeoff checklist. Shortly afterward, the tower gave them the green light. Someone in the cockpit hit the toga or takeoff/go-around button, and the engines came up to max power. At 11:20 p.m. UTC, the first officer calls rotate and the left stick shaker activates. The stick shaker is a warning to pilots that their plane is about to stall. If the stick shaker activates, pilots are required to bring the nose down and thus avert disaster. Moments later, the takeoff configuration warning sounds. The first officer states, "Takeoff config." The takeoff configuration warning sounds when the plane isn't properly configured for takeoff, like if the flaps aren't deployed. At 11:20 and 23 seconds, the plane becomes airborne. As soon as the plane lifted off, they had another problem to add to the list. The co-pilot calls out, "Auto brake disarm." They had a speed disagreement. The first officer's display gave them one speed and the captain's gave him another speed, 173 and 164 knots respectively. The first officer is rightly concerned and asks the captain if he wants to return to the airport, but the captain doesn't respond. As the tower handed them off to Terminal East, the next problem popped up. They now had an altitude disagree warning. Both altitude readings on both sides of the airplane differed by about 230 feet. They contact Terminal East, who asks them to climb to 27,000 feet, which was their cruising altitude for this flight. The captain, who is more than concerned at this point, asks the co-pilot to perform the airspeed unreliable checklist. The co-pilot does not respond. At 11:21 p.m., the first officer asks Terminal East for a holding point, and they tell Terminal East that they're having control issues. As they try to troubleshoot the problem by resetting the flaps, the captain asks the first officer to take over flying, and the first officer says, "Stand by." Meanwhile, the controller at Terminal East can see that Flight 610 is descending on their radar scope. The captain asks for 5,000 feet as they reset the flaps again. Terminal East gives them 5,000 feet and asks them to turn to 050 degrees. As they turned, the bank angle warning sounds. For a moment there, the plane hit 35 degrees of bank. Things are not going well. At 11:22 p.m., they set flaps to 1, and the FDR, or flight data recorder, records the electric trim, moving the trim of the airplane to 4.7 units nose up. At 11:22 and 44 seconds, the first officer calls 5,000 feet. The altitude select in the cockpit was changed from 11,000 to 5,000 feet, and the plane began to descend. It lost about 600 feet of altitude in seconds. At this point, the plane's software trims the nose down for 8 seconds due to the low airspeed it's receiving from its sensors. The EGPWS system chimes in. Airspeed low. Airspeed low. The controller asks for their airspeed, which was 322 knots on their radar scope. The captain, in his desperation to arrest the dive, trims the airplane nose up for 5 seconds. And it works. The plane starts climbing at 1,500 feet per minute. The aircraft nose down trim activates again for a few seconds and the plane descends again. The pilots go through their checklist. The co-pilot says, "Fuel differential already done. Auto brake, engine start switches off. What's the memory item here?" As they did this, the A&D, or the aircraft nose down trim, activates again. It only activated for a few seconds, but it threw the cockpit into chaos. At 11:23 p.m., sounds of paper being turned in the cockpit can be heard. Almost instantly, the sound of the altitude warning was heard. They were at about 4,000 feet right now. The aircraft nose down trim activates again as the plane began to turn to the left. The captain commands a nose up trim and the plane climbs again. The cockpit is now in chaos as the co-pilot can't locate the airspeed unreliable checklist. At 11:25 p.m., the co-pilot finally finds the airspeed unreliable checklist and begins working on it. But the automatic trim of the MCAS system commands a nose down. The captain immediately fights the automation with his own nose up trim for 6 seconds. Again, the MCAS system activates, commanding a nose down. But the captain counters with his own nose-up command. He is struggling with the plane. This goes on for about 3 minutes. The plane noses down. The captain wrestles it back up. The plane climbs. It descends. The cycle repeats. The captain asks the flight attendant to enter the cockpit. He asked the flight attendant to call the engineer. They were going to need all the help that they could get. The plane still dives of its own accord, and the pilots are still fighting the plane. At 11:29 p.m. UTC, the controller at Terminal East asked them to maintain 050 degrees and to contact arrival in an attempt to get them back to the airport. But once again, the plane dives, which the pilots counteracted immediately. Shortly afterwards, the first officer takes over control of the plane and says, "I have control of the plane." They began to work their way back to the airport, talking to the arrival controllers. At 11:31 p.m. UTC, the captain tells arrival that they're basically flying blind as all their instruments are unreliable. The plane is still uncontrollable, rising and falling as the pilots and the plane continue to fight each other. The captain asks for a block altitude of 3,000 feet so that they wouldn't crash into anyone else in the area. The MCAS nose-down commands were hard, activating for seconds at a time. The control columns were registering about 82 pounds of force. 82 pounds of force that the pilot was exerting in his desperate attempt to pull the plane out of his deadly dive. At 11:31 and 46 seconds, the MCAS commands another nose down. They were about 3,300 feet above the ocean, and the plane enters a screeching dive, which is about 10,000 feet per minute. Seconds later, a voice can be heard in the cockpit saying, "Terrain, terrain," and soon after, another one joins the chorus. Sink rate. They were losing the battle, and the plane commanded another nose down. At 11:31 and 56 seconds p.m. UTC, the MCAS system commands a nose down, and this time they didn't have the room to fight back. Flight 610 hits the surface of the sea off of the coast of Indonesia. Arrival tries to contact Flight 610, but they received no response. The pilots of Lion Air Flight 610 had been overwhelmed by the automation that was meant to protect them from stalling. The flight was plagued with problems from the get-go, but this was not the first time. A look at the plane's history brings up its troubled past. On the 9th of October, the plane's maintenance logs show that the plane had an angle of attack signal is out of range problem. On the 27th of October, it had that problem one more time. The plane had a stall warning error and an error that said that the ADIRU, or the Air Data Inertial Reference Unit, was faulty, and that the computer could not trust any data that came out of the left ADIRU. The engineers on the ground tried to fix the problem by reconnecting it and trying a whole host of other methods, but the crew on the 27th of October had problems with speed and altitude. The maintenance technicians decided to fix the problem in Denpasar. On the 28th of October, the plane had a whole host of issues. The auto throttle disconnected on takeoff, and the ADIRU was once again unreliable. On the ground at Denpasar, the engineers tried to fix the issue, but the problem persisted. They tried to reset the circuit breakers of the AC, DC, and the EXC of the left ADIRU, and the problem seemingly was solved. The engineer decided to replace the AOA, or the angle of attack sensor, on the aircraft when maintaining it at Denpasar. The angle of attack refers to the angle between the oncoming air and the plane's wing. If it gets too high, the plane can stall out. The angle is measured by an AOA sensor. As they waited for the AOA sensor to get there, the plane was grounded. When they did get the sensor, they didn't have the equipment to properly test it, and thus they decided to perform alternative tests on the plane and then released it into service. It flew from Denpasar to Jakarta, and the crew had problems with their altitude, speed, and a whole host of other warnings. Sound familiar? After this, they cleaned the pitot tubes and cleaned the connectors of the sensor, and then they released the plane into service. This should have never happened. Looking at the data from the FDR of the flight data recorder, they realized that the issue had not been fixed. On the accident airplane, it showed that the AOA readings on the plane was wrong from the moment it took off. One sensor thought that the plane was climbing, while the other thought that the plane was in a shallow descent. Improper maintenance from the ground crew squandered an opportunity for them to prevent the accident. But how were the previous crew able to land their plane when the crew of Flight 610 couldn't? When trouble struck on the flight that made it back, the captain of the plane asked the first officer to take over, and he assessed the situation. He saw that the speed and the altitude were in disagreement, and that the auto trim had a tendency to nose the plane down. The co-pilot of that flight even commented, "It was too heavy to hold back," meaning that he was barely keeping it under control. The captain noticed that the plane was in trouble, so he fell back onto manual trim, and that made flying the plane easier. The captain of the flight that landed wrote up an issue about the plane's problems, but he left out two important details: the stick shaker and the fact that he had to use manual trim and not auto trim. Had he specified these two facts, the crew of Flight 610 might have had more information going into the flight. The crew of 610 might have tried manual trim instead of auto trim throughout the entire flight. Had they known about the stick shaker activation and the uncommanded nose downs of the previous flight, they might have been more prepared for the troubles of Flight 610. Moreover, the flight crew did not have a checklist for this situation, so they had to rely on NNCs, or non-normal checklists. They never completed the NNC, which meant that they never had a full picture of what their airplane was doing. They had the stick shaker going off in the cockpit, but there were no other signs of a stall. They didn't know about the faulty AOA sensor, so they were completely in the dark. To make matters worse, other versions of the Boeing 737 had an AOA disagree warning in the cockpit, but on the MAX, this was an optional upgrade, and the crew were not alerted to the AOA sensors disagreeing. It's no secret that the crew of Flight 610 found themselves in a situation that not many pilots expected to find themselves in, and it's impossible for a manufacturer to write checklists for everything that can go wrong in a machine that has tens of thousands of moving parts. This is why they have NNCs, or non-normal checklists. which are designed to help pilots cope with edge case scenarios. For a non-normal checklist, you first have to recognize that you are in a non-normal condition and then maintain control, analyze the situation, take proper action, and then evaluate the need to land. Lion Air operational manuals say that the captain must assign crew duties so that they should have a full picture of the situation. If everyone's solving the problem, they might lose situational awareness and inadvertently put the plane into a dangerous situation. In the case of Flight 610, the captain did not verbalize duties. The pilots lacked a shared mental note. Communication in the cockpit broke down. For example, the first officer did not do the airspeed unreliable NNC, nor did the captain follow up on the airspeed unreliable NNC checklist. The first officer and the captain had a disconnect. Both pilots were missing callouts that they should have made. The captain rarely responded in the proper way, and his answers were short. In short, both crew members were engrossed in their own activities, and no one was really monitoring the instruments of the plane. Just to give you a sense of how bad the communication was, the captain never told the first officer about the difficulty in controlling the aircraft and the need for repeated nose-up trim commands. Subsequently, the first officer was not able to anticipate the need for repeated pitch corrections and nose-up trim and did not use adequate electric trim to counter repetitive MCAS activations while controlling the aircraft. This, for me, is one of the most shocking parts of the report. Had the captain told the first officer about the repeated nose-up trims, maybe the co-pilot would have applied more electric trim. Why didn't the captain tell the first officer about this? It's unknown. Maybe he expected the first officer to pick up on this. The plane had been throwing errors for the past few flights, as we talked about earlier. The first hint of trouble was on the 26th of October when the captain's speed and altitude readings were replaced by speed and altitude flags, and the problems continued from there. After multiple problems, the engineers decided to replace the AOA sensors. The engineers could not test the new AOA sensors as protocol dictated, so he opted for an alternative approach. During the investigation, Boeing and the NTSC investigators did the AOA replacement on a similar aircraft with a flawed AOA sensor. After the replacement, the investigators found that the AOA sensor did not pass the test to see if it was fit for service, but the engineer certified the plane for operations anyway. Now we're going to take a look at how the MCAS system impacted the plane. This has been the most talked about feature and focal point of controversy for well over a year. The 737 MAX is a derivative of the 737-800. The MAX has newer and wider engines. The wider engines, Boeing realized, would impact the plane's handling in a negative way, so Boeing implemented aerodynamic changes and added MCAS to the speed trim system. MCAS made the plane more stable at high angles of attack, and MCAS made the plane fly similarly to the 737-800, so pilots would not need simulator training to fly the 737 MAX coming from an older 737 version. During MCAS development, Boeing considered the possibility of a runaway MCAS activation, but they never did test for erroneous AOA sensor readings. When testing, they didn't test high elevator deflections at high speed, and also Boeing didn't test for repeated MCAS activations. According to Boeing, repeated activations could be countered with trim by the pilot. When Boeing tested the MCAS system, they made a set of assumptions. I want you to look at the first and the last one. The crew of Flight 610 failed these two assumptions. Boeing assumed that uncommanded system inputs were readily recognizable by the flight crew and that they would react in a short amount of time. The crew also failed to carry out checklists that were designed to mitigate the issue that they were facing. In Boeing's simulator tests, they found that a MCAS activation can be countered with elevators and stabilizer trim, and cutouts can be used to help fight the situation. In the report, they say on multiple occasions that the MCAS activations can be countered by the use of trim and control input, but the first officer never applied enough trim to save the plane, and the plane was doomed. The Boeing 737 MAX has two angle of attack sensors, but the MCAS system only uses the data from one sensor. This means that if one sensor were to fail, the flight computers would be fed corrupt data, and that could lead to erroneous MCAS activations. Boeing said that AOA failures were rare, with 25 AOA failures in 240 million flight hours. Using data from both sensors would have been the right way to go, but certification didn't mandate that Boeing use both sensors. Also, Boeing revised the MCAS system to give it more authority. Initially, the MCAS system had a control authority of 0.6 degrees, but it was later revised to 2.5 degrees to help deal with low-speed flight. This meant that at low speed, the stabilizer deflected a lot more, and that meant that the nose would pitch down a lot more. If the MCAS system activated, pilots could still override it by switching to manual trim or by compensating it with electric trim. At 2.5 degrees of control authority, 2 activations of the MCAS system would be enough to put the plane in a nosedive, assuming that no evasive action was taken. Against all odds, the AOA sensor malfunctioned, and the crew did not act in the way Boeing expected them to. In short, this is what brought down Flight 610. A faulty AOA sensor that was not fixed by the ground crew sent corrupted data that made the computer think that the plane was about to stall when it wasn't. Due to no redundancy of the AOA sensor, the MCAS system activated trying to bring the nose down from a stall that the plane even wasn't in. Due to bad crew resource management, the captain does not tell the co-pilot about trimming the plane. The primary flight display does not have an AOA disagree warning telling the pilots that both AOA readings disagree. Had the pilots had an AOA disagree warning, I think the outcome would have been a lot different. The pilots never did understand that the faulty AOA sensor was the root of all their troubles. It also breaks my heart to realize that no one told the pilots about the AOA troubles that the plane had been having over the past few days. The co-pilot, who was now flying the plane, does not apply enough trim, and the faulty MCAS system puts the plane into a steeper and steeper dive till it crashes. A lot had to go wrong for this crash to happen. Bad software from Boeing, bad crew resource management, and bad maintenance. It's easy just to place all the blame on Boeing, but it's imperative that we look at all the other flaws as well. If we don't, it's only a matter of time before another plane goes down due to one of these reasons. It's imperative that we learn from these mistakes and make flying safer. Thank you for watching this episode of Mini Air Crash Investigation. A big thank you to MYLOSAIRPLANEFAN for letting me use his amazing videos on my video. If you like the videos that I make, do consider liking and subscribing. It really helps the channel grow. I'll catch you guys next time.